Are we ready? Like, cool. I'm really happy to see you all here, and I think it's really cool that last years there are so many hype around functional programming, and like we really try and to build a lawful software, a software that just runs. How many of you actually are doing functional programming every day? Wow, really cool. And like, does anybody want to do it every day? So it looks like already a lot of people are doing it. And how many of you used FS2 already? Or and other streaming libraries like Arca streams? Cool. I will try to go through basic combinators, and I think there are combinators that looks a bit differently than in Arca streams, but which have the same semantics or the same meaning. That will be the agenda. I think what is really cool in FS2 is that it basically have an IO monad, and it describes explicitly the effects, which is very different in Arca streams. So I will try to do a quick intro, then I will try to cover basic combinators to build a stream, to transform a stream, and to bake an effect into a stream. I will quickly show how to do a logging. It's not in obvious way, I mean not in the way that you saw it in imperative languages or more imperative streaming libraries. I will quickly explain what is chunks and segments, what the purpose of them. Error handling, resource acquisition, which is done as well very explicitly. Combinators which support concurrency. And I think I put the abstraction as almost the last point, because I think where really functional programming shines is taking small pieces and building a bigger program with them. Small lawful pieces which guarantee you that everything's fine, everything will be run as expected. And I think for most of the guys that really are experienced with the streams, only the 10th part will be really interesting, because there I will try to show how I try to make a Dynamo imperative APIs to be streamed-like. Okay. Am I too slow? It's fine. So a lot of examples are taken from official documentation. So if it seems familiar, maybe it is. So a basic intro, like why do we really like a functional programming? Because it's all about functions, right? Functions which are total, meaning that for each input you will get an output, which are deterministic. So that means that if you give a function the same input, you will always get the same output. And that they are pure, meaning that function is only do what described in its type and nothing more than that, which basically enables the very powerful tool which is called local reasoning, which basically gives you ability to concentrate on that piece of functionality and like abstract away all the noisy worlds which around this function. And FS2 basically gives you a lawful algebra to deal with potentially unbounded or infinite streams of data. And there are two ways basically now in which the streams are implemented. One is push-based, and the most famous one is the observable pattern, when you basically register the subscriber together with the observable, and then observable is basically pushing the messages to the subscriber or invoking it directly. But in contrary, the FS2 is pull-based, which means basically that downstream will pull messages from the upstream service in a pace it basically can deal with the messages. And what does this mean? That, for example, you don't need to think about things like a back pressure, because like it's an obvious way, because since the downstream is asking for messages, not upstream pushing the messages, downstream knows better how many messages it can process in the next moment and take only that amount of messages that it basically can process. So let's get a little bit more technical. This is basically the type of the stream. And here we see that it describes the effect and the type of the elements that the stream will basically produce. I will then show you a little bit how all of this stuff works. So the first several combinators are to build a stream. So you can build an empty stream, of course. You can emit a message or build a so-called singleton stream, which only emits one message. You can, of course, emit a sequence of elements, or you can use a Plea, which build a stream as well. So you can see that for all of these streams, the effect type is a pure, which means that it's basically effectless in the moment. And if you have effectless stream, you can just convert it to the regular collection, which is fine. It had, of course, a basic collection combinators, like you could, of course, repeat and take sorry, I should repeat it. Yay. So it's repeated 2 times and 6 elements was taken from it. You could, of course, do all the regular stuff like map +1 and do a list. So you can do all the stuff. You can concatenate them, of course. You can filter them. You can fold over them. All the basic stuff. But it's not that interesting. Much more interesting it becomes when you can bake an effect into a stream. And this is basically the most useful operators or most common operators when you can deal with effects. So we can do, for example, whatever we want. 1 and 1. if you will try to do the toList, it will not work, or not in a understandable way. You can do something like this. Yeah. So what you this combinator basically takes an IO and as an effect and give you ability to bake this effect into your effectful stream. And here you usually use several combinators. And compile is basically prepare the stream to be evaluated, because the stream at the end is just a bunch or a list or a collection of effects, and sometimes you are interested in the results of execution of events, sometimes not. If you are interested, you will use something like toList, saying that I would like to get at the end the list of outputs, or you could use something called drain, which means that I don't care about what will be the output. It basically means that you will, of course, sometimes execute only for side effects. For example, if you try to write something into into database, whatever you want, you don't really interested you're interested that it was written, but you are not effectively getting something from database, for example. Then you will be doing toList and give me something. Another combinator was as well eval, which converts a stream of effects of something to a stream of effects of nothing. Like in a case as well, when you are not interested in the results of materialized results of the stream evaluation. So there are some other combinators like eval map, and if we will take a look. So there are effectful combinators that gives you ability, for example, to build a effectful stream from a function which takes something and returns you an effect which, when evaluated, will return you a stream. And kind of stuff. So the FS2 is basically built to work with any kind of effects, but I will try to show you, or I'm using only the implementation of Get's effect library. And this is basically the way how you can rob or how you can create an effect, which is an IO effect. So you could use IO pure and do something like this. Usually, you should be pushing any effects to the borders of your applications and invoke it on the end of the application. And basically, all of this stuff means that at the end of you will get and basically IO. So this combinator here, it is defined on IO. That means that all these combinators before are basically prepare or build an effect at the end, which you are executing and getting some side effects and some elements. What? Yeah, so this was one. Pure is only meant to be used for the values that are already evaluated and you just need to emit them. If you are using apply have a meaning of delaying the operation. If you have, for example, some side effect, which is 1, then 1, and then you say save. So you build the effect which will bring something to the output stream and which will return the 1. And there is of course a combinator to evaluate effect not in the same thread pool but in another thread pool or just asynchronously, and it's called asynchronous async, and it looks very interesting. So it takes an either, and this either is a callback which you should call when you build some computation, you run this computation, and you invoke this combinator only at the end of your computation. And what it's doing is basically like injecting the results of your computation back into the mainstream. And the one of the most important one is a shift. In the previous versions of I/O, it was into the I/O abstraction, but now they move it to the async companion object. What is basically doing is you usually in your application you need to have several thread pools, and one of them should be unbounded thread pool for the blocking operations. And when you're using shift, you're basically saying that, okay, now I have a blocking operation. Please take this computation and put it into another thread pool, which is meant to be used for the blocking I/O operations. But it's very mechanical operation, so when computation, you need as well define that you need to shift back when computation is ready. If I'll have enough time, I will show you this on the real application. This is basically the way how to do a login, and login is done with observe. Just wanna find really simple example, like this one, for example. The combinator is called observe. It takes the sync, and sync is a pipe which converts a stream which emits a values to a stream which emits nothing, basically. So it's like sync values. Like there are already predefined syncs. For example, for the I/O. There is a very useful combinator called covary. In case if you have a string which have an effect of a pure and you would like to conform to any other effect, you could just define in covary what effect this would be. In this case, for example, it would be I/O because we only use an I/O. And when you are doing thing, you're defining as well what effect do you use and what values you will sync. And in this case, this will be an int. So it's something like that. And then sync. But before we need to compile it and say that we don't care. Yeah. It says just that it doesn't like the effect type, and that it could not, doesn't know how to convert any into the string. And did I? Huh? Mm. Yeah, so you need to use observer. So chunks and segments, and by semantic of FS2, segment is representation of infinite collection. On the previous version of FS2, they used array, which is unbelievable. Like you cannot talk about the unbounded stream and the same time use the arrays for representing them. So they come up with this idea to have a segment, and segment basically by its type represented with as well effect and a stream that and elements that inside it. And chunks is basically an opposite to the segment, which define the finite collection of an elements. And you could of course get back and forth from chunks to a segments, but usually it's not. It's better not to try to force a segment, because if you understand that it could potentially be infinite, when you will try to force it, it potentially would not stop. So it will run infinitely. So this basically, there are a lot of combinators in FS2 which are segment error, because segmentation is basically a way to group the elements, so a way to batch them and process them in next step in kind of groups. It becomes very useful when, for example, you need to group elements explicitly, for example, for the batching operation, to save elements into database in a batches, for example, or to when you call in some API and you use an IDs and you kind of say segment 3 elements or 5 elements and then build an URL from them and then execute it. So this is basic combinators which helps you to raise error and handle error. So here you can see basically that I am trying to raise an error, then I am handling the error, and it really looks like a Flatmap function, which is basically take the should exception, takes a message from it, and emit it further as a stream, which in the Flatmap semantic means that you just transform the stream. So you kind of transform the stream of throwables into a stream of messages, in case there was something thrown. And at the end, you of course get a vector with a message inside. And of course, it will be interrupted as soon as a message with the error of a computation that through the error, it will basically halt the computation and end up with a message in this case. There are a combinator which called bracket, and the main idea of it is to acquire a resource, and you basically defines here the resource you would like to acquire. For example, in case of AWS API, this could be a client. Then you define a function where you take this client and do some transformation or do some querying or whatever you would like to. And in a release function, you basically take the same resource you acquired, like Amazon client, and you need to shut down it. So to free the resources. It's usually a very useful one. And this basically the combinators that enables or support the concurrency. For example, the merge. The merge is something which, if you have a stream and you have another stream, you could merge them, and as a result, the values will be emitted when results from one stream and from another stream will be available. Either do exactly the same, but it emits the others. So if you have two streams which, after evaluation, produce some elements, these elements could be of left or right. So meaning that when this effect was executed, it correctly produced a result, or it failed when it was trying to produce a result. And join is something that is there when you have an defined amount of streams which you would like to execute in concurrent manner. You just define a stream of stream basically and say that I would like to execute or evaluate that amount of streams concurrently, and you put here basically the value of which is most probably supposed to be the number of CPUs on your machine. And this is like the last slide, which I find really cool because it really shows you how having the small abstraction you could build a bigger abstractions. By that I mean that a pipe, which is basically a transformation defined as a function of one stream producing one result to convert to another stream which producing the other result, which is of course a transformation. The pipe 2 is kind of fan-in when you have two streams with potentially which producing a different kinds of elements. The pipe will be like fanning out or taking both of them and creating a third one by combining this parallel to which could be very different one. And think is something that a pipe which takes an E and like pipe, we know that it's transformation. And in this case, it basically, when it evaluating the stream, it takes elements of type E and produces the elements of type units. So that basically syncing the values, like doing something with them, but meaning that you are not interested in the results. So you are purely executed for some side effects. This is some references, which I think are very cool, and one of them is the documentation, which is very broad and explains all the details and how to use them. There are really cool article from Daniel Spivak where he explains what is an I/O monad, how does implementation of CATS I/O looks like, and this is the videos for Michael Plequist. I can be wrong with the surname, which is as well really cool. So yeah, it's basically all the things I would like to show. I can, if there are interests, I can show how does this look with DynamoDB. So would you like guys to see some code? Or yeah, that's it.
Maybe some questions?
Yeah.
So you showed us several examples of the code where you do shift in to IO, and question is there like is there a way to kind of put that aside? I mean like it's obviously like important to do this IO on a separate like executor or something, but it kind of like you have this your business logic or something, and then you're like, oh, I need to like shift here. Can you just write it execute on this thing and then get back to main or something? I mean,
Yeah,
do they provide anything like that?
So it's very mechanical operation. It's very explicit operation. So if you know that this operation is blocking, you're doing a shift to another executor pool, but then you need to explicitly shift back.
Yeah, that's what I'm saying. Like like you would use like any kind of lawn pattern or something like that. Oh, just use this thing, but then go back to the previous state or something. So that you don't like, because you always like shift to something and then shift back.
Yes.
To where you were usually, right? So is there any like shortcut so that you don't have to do that like everywhere?
I don't know anything like that, but you can of course try to use, for example, the bracket.
Okay. Makes sense. And another quick question. I know this sort of like convention, but do you get any questions like, oh, why do you say like implicit f colon and then effect of another f? You have like f twice, and they're different f's. So like, do you get these questions often, or?
It's the first time I'm presented.
No, I mean like you're not the only developer of this project, right? Are there any other people who just you shown this code and they like it doesn't look confusing? Because I mean, to me, I know there's a convention in this community to do things like that, but to me it always looks confusing. Like name the instance with this like uppercase, and I don't know.
Yeah, I honestly I think that is a little bit confusing, because sometimes you have 2 times f, you have f as variable, and you have f as a type.
That's what I'm saying. Like here, it's like the f is a type constructor.
Yeah,
here it's like f is a type constructor and f is a variable, and that looks a little bit confusing.
Yeah,
at least to me.
I didn't get yet this question, to be honest, but I find it as well confusing, and but I don't know what it's like. I have no opinion.
Okay, so thank you for questions. It's all.